Okay, so let's see this next one. Here we have to prove that the relation of two groups being isomorphic to each other, that is, the relation which is brought about the notion of isomorphism is an equivalence relation on the class of all groups. So that means we have to show that the relation is reflexive, symmetric and transitive. Reflexivity demands that any group is isomorphic to itself. Symmetry demands that if G is isomorphic to H, then H is isomorphic to G. And transitivity demands that if G is isomorphic to H and H is isomorphic to K, then G must be isomorphic to K. So let's see how this can be proved. It's actually quite straightforward. So it's given that G, H and K are groups. So first we have to show that G is isomorphic to itself. That means we have to find an isomorphism from G to itself. And one such isomorphism, there may be many such isomorphisms, but among them one is always there, and that is the identity isomorphism, which actually becomes an automorphism. So that is this. Consider the identity map F from G to G defined by this formula. Now we already know something about the identity map, that it is both one-to-one and onto. We know that F is one-to-one and onto. So we just have to verify that other condition for it to be an isomorphism. For any two elements G and H in G, we have F of GH. By the definition of the map F, it is nothing but GH itself. But then again by the definition of F, G is nothing but F of G and H is just simply F of H. Hence, F is an isomorphism, and so G is isomorphic to itself. So that is 1/3 of this solution. Next, let G be isomorphic to H. Then there will be an isomorphism from G to H. Then there exists an isomorphism, say we call it G, from G to H. Now being an isomorphism, as a mapping G is one-to-one and onto, that means it's bijective. since G is a bijection, its inverse G inverse, which is a map from H to G, exists. We will now show that this G inverse is also an isomorphism. Now we already know that whenever G inverse exists, and that is when G is bijective, G inverse itself is also bijective. It's a property of inverse maps. We know that G inverse is a bijection. Then we have to verify this property also for the map G inverse. Oh, okay. Let me just use another symbol because we already have taken G here. No? So let me call it G prime. Then G prime inverse, G prime inverse. Okay, now we have to verify this condition for the map G prime inverse. So keeping in mind that the domain of the map G prime inverse is H, is the group H and not G. So we are going to consider two elements, say A and B in H. Okay. Then G prime inverse A, because A and B are elements coming from the group H, so we can apply the map G prime inverse to these elements. Then these are going to be elements in G. There is a heavy rain going on outside, so there is some noise disturbances. Okay. Now you consider these two as elements. Well, they are elements of G, but now you consider them in place of G and H, and use the fact that G prime itself satisfies one such condition because it is an isomorphism. Since G prime is an isomorphism, so we have this. If you calculate this using the fact that G prime is an isomorphism, you are then going to get this. And because this G prime and G prime inverse, they will give you the, they will cancel each other. So you will be left with AB. Now note that the G prime image of this product is AB. So from this equation we can write next this. G prime inverse of AB is equal to G prime inverse of A times G prime inverse of B. Do you see how we are concluding this from this one? Because the G prime image of this is AB. So the G prime inverse image of AB will be this. That's what we have written. But now you see what we have achieved here. A and B were some arbitrary elements in the domain of G prime inverse, and we have applied the function on their product. So the function has gotten distributed over A and B. So this now shows, along with the fact that this is a bijection, that G prime inverse is also an isomorphism. Hence, is an isomorphism. Hence, so but G prime inverse is the function from H onto G. So H is isomorphic to G. We have thus proved that this relation of two groups being isomorphic is reflexive and symmetric. So now only we have transitivity to prove. Next, let G be isomorphic to H and H be isomorphic to K. So now we will get two isomorphisms. Then there exist isomorphisms say we call them alpha and beta. Now we are seeking an isomorphism from G to K. So what can be more natural than considering the composition of these two functions? Consider the composition of alpha and beta, which maps G into K. Now from the properties of compositions of mappings, we know that since alpha and beta are both bijections, so their composition is also a bijection. Since these are both bijections, so is beta composition alpha. So now next we have to verify that condition for this composition. So let us consider two elements C and D in G. Then if you apply this composition on the product CD, then by the definition of composition, this is the beta image of the alpha image of CD Okay. Now first you use the fact that alpha will distribute itself over the product because alpha is an isomorphism. So this equals beta of alpha of C times alpha of B. But because alpha of C and alpha of D are elements in H, and H is the domain of beta, and beta is also like alpha an isomorphism. So now beta will get distributed over the product. Beta of alpha of C times beta of alpha of D, and this finally gives us what we want. Thus, this is an isomorphism and we have G isomorphic to K. So we have completed proving that the relation of two groups being isomorphic is transitive as well, and that is why it's an equivalence relation. So you can write the final conclusion. I am ending the solution here itself. Let's see the next one. Prove that the symmetric group S4, symmetric group of degree 4, is not isomorphic to the dihedral group D12. Now, in this kind of problems where you have to prove that two groups are not isomorphic to each other, you have to see if some necessary condition is being violated, which is a consequence of two groups being isomorphic. When two groups are isomorphic, some consequences are there of that. So if any such consequence is violated, then the two groups cannot be isomorphic, and that's how we are going to solve this. It's quite easy. If you recall from our previous knowledge about these two groups, this group has the trivial center. That means in its center you only have the identity element, but the center of this dihedral group has two elements. And we know that one of the consequences of two groups being isomorphic is that their centers should have the same size, which is not the case here. So that's why they cannot be isomorphic. We know that the order of the center of S4 is 1. And the order of the center of D12 is 2. So let me refer that result also by theorem 6.2. In fact, this theorem has some parts, right? You look at the last part, there you have something about centers of isomorphic groups. D12 or S4 is not isomorphic to D12. That is the reason. Because they have centers of different sizes, so they cannot possibly be isomorphic. Next. Show that the mapping A to log a but with base 10, not natural logarithm, but base 10 logarithm is an isomorphism from the set of positive real numbers which is a group under multiplication. To the set of real numbers which is a group under addition. Okay. So here the mapping is given, so we just have to prove that it's an isomorphism. Now we already know something about this map, namely that it is a bijection. We know that the mapping, the author hasn't given this mapping any name, so actually its name is log, but let's also name it something else. Know that the mapping, let's call it F. Defined by f of x equal to this is a bijection. This is something you should know from real analysis or even calculus. In calculus itself, we come across this fact that this map is a bijection. In fact, if you want to see how the graph of this looks, it is roughly like this. So what happens is that x should be positive. Only positive real numbers have logarithms that are also real numbers. And the reason for that comes from the fact that the outputs of any exponential function is never negative. Also, it's never zero. That is why. Is something like this. If you put x equal to 1, you are to get 0. So that means 1, 0 is a point on the graph of this function. Just from the graph itself, you can see that the domain is the set of positive real numbers, because the graph does not lie on this side of the y-axis. And in fact, it also does not touch the y-axis. That's because at 0, this function is undefined, which also comes from the fact that the exponential function never becomes 0. Even when the base is 10 to the power y, say, it never becomes 0 for any real y. Also, it never becomes negative. So that's why the domain here is only the set of positive real numbers. That is this. This is your domain. And although the function grows at a much smaller and smaller rate, and the rate keeps getting smaller and smaller as we increase the value of x, but still it exceeds everything eventually. So the range is the set of real numbers. All the real numbers are going to appear as outputs at one stage or another. One more thing that you can see is that it's a one-to-one function. Onto-ness of the function comes from the fact that the graph falls below the x-axis without any bound. Also, it grows above the x-axis also without any bound, although the rate of growth keeps decreasing, but it grows, and that growth never stops. So that gives us onto-ness. But what about one-to-one-ness? One-to-one-ness means that for two different inputs, you will never get the same output. That's because any horizontal line you can imagine, it intersects the graph at precisely one point. Only if you have graph going like this or like this, you will have the same y value for multiple x input points. That you don't see here happening. Of course, this cannot be the justification for the claim that this is a bijection. It has to be proved, and it comes from properties of this logarithmic function, which are rigorously proved in calculus or real analysis. So this is something that we consider, that we already know. Okay. So now we verify that other property. This should not be considered as a part of the solution. It's only for our own understanding. So I can continue from here itself. For any two positive real numbers, we have f of x, y. Here we are considering x, y, and this x, y is actually ordinary multiplication of real numbers. Why? Because this is a group under multiplication of real numbers. So that's why we have x, y. But then you recall one of the very important properties of the logarithmic function, regardless of the base, that when you take the logarithm of a product, it becomes the sum of the logarithms. Which is f of x plus f of y. Now since this plus is the binary operation of this second group, so that's why this f becomes an isomorphism. Hence, f is an isomorphism. So group theoretically there is no distinction between the positive reals as a group under multiplication and all the reals as a group under addition. It seems very strange, but that's the way it is. Okay, next. So which also means that if you study one of these groups, then you automatically know everything about the other group. And what can I say, the path that you should take in order to translate whatever you know about one group into whatever you correspondingly you should have about the other group, that path is this isomorphism. Next. Exercise 6-9. in the notation of theorem 6.1 prove that TE. So in the proof of this theorem, we encountered these functions TG. TE is the identity and TG inverse is T suffix G inverse. So accordingly, we are also going to mention this theorem. We know from the proof of theorem 6.1 that for any G belonging to G, the map or the mapping TG from G to G is defined by left multiplication by G. Yeah, that's what it is. So what we are being asked here is to prove that TE is the identity map on G. That if we apply TE on any X, we are going to get X back. And TG inverse, it turns out that for any G, this map TG is actually a bijection. So its inverse exists. And that inverse we have to show is nothing but another such map where it is the map for the element G inverse. Okay, so let's see. First we show that this is the identity map for which one can almost immediately see why that is the case. We see that TE of X is EX that is equal to X. Hence, TE is the identity. And if you are thinking that by identity the author means not just the identity map on G, but rather the identity element in the group of all bijections from G to itself, then that also is true, because we know that that identity is also actually the identity map, nothing else. Okay, so this much is enough. Next, let G belong to G. We know from the proof of theorem 6.1 that TG is a bijection. So that means its inverse exists. As the inverse of a mapping, it exists. So this exists. Now, for any x belonging to G, there exists a unique y belonging to G such that Tg inverse of x is equal to y. Obviously, this implies x is equal to Tg of y, because in fact that is the definition of Tg inverse, and we already know what Tgy is. It is nothing but Gy, and this in turn implies that y is equal to G inverse x, and which is nothing but the Tg inverse image of x. Okay, so now if we combine this with this, we get this. Thus, Tg inverse of x is nothing but Tg inverse of x. Now, since x is any arbitrary element, any x in G, so this fact is true for all elements in capital G. So as functions, this inverse function and this ordinary function Tg inverse are actually the same thing. So since you can mention that since x belonging to G is arbitrary, this is equal to Tg inverse. How nice this one looks. This inverse, which is the inverse of a mapping, ultimately turns out to be this, and here this is the inverse of the original element. Okay, so that's the solution. Next, let us see another one. Let G be a group prove that the mapping alpha of G equal to G inverse for all G in G is an isomorphism if and only if, so this is a necessary and sufficient condition, if and only if G is abelian. So that means we have to show two implications. One, when you assume that this is an isomorphism, then you have to prove that G is abelian, and the converse. So let's prove the converse first. Let G be abelian. But even before we do anything, you note one thing, that this mapping as a mapping from a group G to itself is actually well defined. Why? That's because if you take any element G as your input, then the first observation is that its inverse exists. So that is the first thing which comes from one of the group axioms, and the second thing is that that inverse is unique, which is a consequence of the which is one elementary property of groups. So because of these two things, alpha is a well defined map, and so it is actually a mapping. And now we have assumed that G is abelian. We now have to prove that alpha is an isomorphism. Actually, it's an automorphism. Yes, because the group is same, it's an automorphism. So let G be abelian. Then for any two elements A and B in G, we have alpha of AB equal to the inverse of AB. Now we know from elementary group properties that this is B inverse A inverse. But because we have assumed that G is abelian, we can write it as A inverse B inverse. So this is nothing but alpha of A times alpha of B. So one of the conditions for alpha to be isomorphism has been verified. Now we need to prove that alpha is bijective. Okay. So for that, let C and D belong to G such that alpha of C is equal to alpha of D. So that means we have considered two inputs for the function alpha, for which the outputs are the same. There is only one output. Now we have to prove that the inputs also should be the same. That is, C is equal to D. That's what we have to prove. Either you do this or you do this other equivalent thing, that in the beginning itself you assume that C and D are not the same. Then you have to prove that alpha of C and alpha of D are not the same. It is up to you to decide which one you want to use to prove that alpha is injective. Sometimes this is easy, sometimes that other thing is easy. So let's see what we get. Then C inverse is equal to D inverse, which implies that their inverses are also equal. And note carefully that you are able to write this from this precisely because alpha is well defined. So what you are actually doing here is that you are again considering the alpha images of C inverse and D inverse, not C and D that we have here. You are again calculating the alpha image of C inverse and the alpha image of D inverse. Now since they are the same input, so the output should also be equal, because otherwise it won't be a function. So you now have this. Or again, we know another thing from elementary properties of groups, that this is nothing but C and that one is nothing but D. Hence alpha is injective or one-to-one. Also, for any, say, Z or Z belonging to G, this is equal to this, which is the alpha image of Z inverse. So this last part tells us that alpha is onto as well. So now we have all the pieces to be able to call alpha an isomorphism, actually an automorphism. Hence, so this is 1/2. Now conversely, let alpha be an automorphism. Now our aim is to prove that the group is abelian. So for that, let us consider any two elements. Say, actually you can consider A and B also, but because we are for some reason considering different things, so what should I take? Let me consider U and phi. Now using the fact that alpha is an automorphism, you get this. Now what does this imply? It implies, if you just apply the definition of alpha, you get this, which itself implies what? Phi U inverse. Note that here we are not doing anything other than the fact that we already know that in any group this is equal to this. We are not using the fact that G is abelian. In fact, that's what we are trying to prove. So you cannot change the order of any product. But in this case, because we have inverses, so we are able to write this. Okay, now you know what you have to do. You have to now just take again inverses on both sides. So that's it. This is our consequence that we want. Hence, G is abelian, and this completes the solution. And let me just stop here itself for tonight. We are going to continue with more exercise solutions in the next Gallian update. And tomorrow, of course, we have another upload which is on analysis. So tomorrow we are going to fill those gaps that we left in the proof of Riemann's theorem in the previous video. Last Sunday I wasn't able to film because I was not well, but now it's okay. So tomorrow we are definitely going to see those gaps being filled. So see you tomorrow. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.